Hello, everybody. Did anybody have any questions for us to get started with? All right. Then if you don't have questions, okay, can you guys see my screen where I've got section 6.6 notes? And you can hear me? Good, okay. So we're gonna take a look at section 6.6. And 6.6 is about
I grabbed them.
What? Oh no, they're so unhealthy.
Section 6.6 is about solving trigonometric equations. Hang on just a second. Okay, I think we're good. All right, and so the goal in solving trigonometric equations in one variable is to find the values for that variable which make the equation true. All right, so just like solving equations back in algebra class, we're trying to figure out what values of the variable will make the equation true. So we're going to start with an example. It says solve cosine x is equal to 1 on the interval where x is an angle between 0 and 2 pi. So can you think of any values for x that we can use? So there's a couple solutions. There's x equals 0, and there's x equals 2 pi, right? So on that interval, there are two solutions. And since there's more than one solution, anytime there's more than one, there's going to it does not have a unique solution anytime there's more than one solution. Okay, so if there's more than one solution, the equation does not have a unique solution. So in general, trigonometric equations don't have unique solutions.
Is there ever a time where they do have a unique solution?
Well, it would kind of depend on the interval. So for example, if I said to solve this equation on the interval from 0 to pi, then there would be a unique solution. The only answer would be 0. Okay? But in general, we don't really want to limit anything. So I would say that in general, there will be many solutions because we won't be limiting ourselves. Does that make sense? Okay, so we looked at solving cosine x equals 1 on this particular interval. That was part A. For part B, we want to just solve cosine x equals 1. So now there's no interval restriction. So there's going to be a lot of different solutions, right? We already know a couple of them. So there's x equals 0, x equals 2 pi. There's also negative 2 pi, 4 pi, negative 4 pi, 6 pi, negative 6 pi, 8 pi, negative 8 pi, 10 pi, negative 10 pi. I could just keep going forever and ever, right? So when we have a situation like this, it's going to be helpful if we can just write down a general formula. So I notice that basically what I've got is I've got multiples of 2 pi. So I could write that as 2 times pi times n, where n is an integer. Right? So if n is 0, that would give me my first solution of 0. If n is 1, that gives me 2 pi. If n is negative 1, that gives me negative 2 pi. Right? And I'll be able to get all of these solutions by just plugging in integers for n. Any questions so far? Okay, so now we're going to take a look at part C. Part C says we're going to solve the equation sine of 2x equals 0. So I'm going to think, well, what could the angle be? So sine of what equals 0? So we could have 2x could be, I know the sine of 0 is 0, so 2x could be 0. I know the sine of pi is 0, so x could equal pi, or it could equal 2 pi, or negative pi, or negative 2 pi, or 3 pi, or negative 3 pi. Right, we have 4 pi, negative 4 pi, and so on. So that could all be what I would plug in for my angle 2x. So now that we know what 2x could be, what could x be? I just want to take each of these answers and divide them by 2. So x could be 0, could be pi over 2, could be pi, could be negative pi over 2, could be negative, let's see, where am I at? So I just did negative pi over 2. So negative pi, 3 pi over 2, negative 3 pi over 2, and so on, right? I just took each one of these answers up above and divided by 2. So now what pattern are we noticing? Okay, we're noticing that this time we don't just have the multiples of pi, we have the multiples of pi over 2. Actually, I'm sorry, we don't have the multiples of 2 pi, we have the multiples of pi over 2. So we can say that we have n times pi over 2, where n is an integer. So for example, if I plug in 0, that would give me 0. If I plug in 1, that would give me pi over 2. If I plug in 2, that would give me pi. If I plug in negative 1 for n, that would give me the negative pi over 2. If I plugged in negative 2 for n, that would make the negative pi. If I plug in 3 for n, that would give me 3 pi over 2. And if I plug in negative 3 for n, that would make the negative 3 pi over 2. So I'm going to be able to get all of the different answers by just plugging in different numbers for n. Any questions so far? All right, so now we're going to take a look at solving some different equations. We're going to start with solving 2 sine x minus 1 equals 0. And I'm going to start by figuring out all the answers on the interval from 0 to 2 pi. So the first thing I'm going to do is I'm going to add 1 to both sides. So I have 2 sine x equals 1. Okay, just like if you were trying to solve 2x minus 1 equals 0, the first thing you'd do would be to add the 1 to both sides. And then the next thing is to divide both sides by the 2. So we get sine x is equal to 1/2. Okay, and then you need to think about your unit circle. So where on the unit circle would the sine of x be equal to 1/2? And there's a couple different answers. There's one answer in quadrant 1 and an answer in quadrant number 2. So the answer in quadrant 1 would be x equals pi over 6. And the answer in quadrant number 2 would be x equals 5 pi over 6. Does that make sense so far? Okay, so now that we've figured out the answers in the interval from 0 to 2 pi, about all the answers. So we know that there's one solution. I'm going to go ahead and just rewrite this down below. So x equals pi over 6 or x equals 5 pi over 6 are the answers between 0 and 2 pi. Okay, so from the smaller angle, I know that pi over 6 is an answer. And if I went all the way around the unit circle and landed on pi over 6, that would be another answer. So we would have x equals pi over 6, pi over 6 plus 2 pi. We could do pi over 6 minus 2 pi. We could do pi over 6 plus 4 pi, etc., right? So we can always start with one answer that we know and add on 2 pi or subtract 2 pi or add 2 pi twice or subtract 2 pi twice. So we get a general formula, and it's going to be pi over 6 plus 2n pi, where n is an integer. Does that make sense? Okay, and then we have our other solution. Our other solution was x equals 5 pi over 6, but we could also do 5 pi over 6 plus 2 pi, or 5 pi over 6 minus 2 pi, or 5 pi over 6 plus 4 pi, or 5 pi over 6 minus 4 pi. So that's going to give us a general solution of 5 pi over 6 plus 2n times pi, where n is an integer. Is that all okay so far? Any questions? Okay, next, we're going to take a look at solving a quadratic trigonometric equation. So you might be able to look at this and factor it the way it is. If you can't factor it the way it is, one thing that you can do is you can use u as cosine of x. So if u is cosine of x, then u squared would be cosine squared of x. So this equation would turn into 2u squared plus u equals 0. So now that we've written that as 2u squared plus u equals 0, can you see how to factor it? Yeah, this is similar to u substitution, yeah. Okay, so we would factor this as u times 2u plus 1 equals 0. Does that look okay? So now we're multiplying two things together, and we know that when we multiply them together, they equal 0. So either u equals 0 or 2u plus 1 equals 0. Okay, so u equals 0. I'm not going to do anything with that yet. that 2u plus 1 equals 0, that means that 2u is equal to -1. And that means that u is equal to -1/2. That makes sense so far? And now let's remember what u was. U was standing for the cosine of x. So if u is equal to 0, that means the cosine of x is equal to 0. And if u is equal to -1/2, that means the cosine of x is equal to -1/2. Does that make sense? And if cosine of x is equal to 0, well, we know that x could be pi over 2 or 3 pi over 2, right? We have the top of our unit circle or the bottom of our unit circle, or we could add on, we could add 2 pi onto each one of those. So we would have pi over 2 plus 2 pi. We could have 3 pi over 2 plus 2 pi. So that's going to give us, in general, x is equal to pi over 2 plus 2n times pi, or 3 pi over 2 plus 2n times pi, where n is an integer. So those are the solutions for cosine x equals 0. Now let's think about cosine of x is equal to -1/2. And on our unit circle from 0 to 2 pi, there's 2 different answers. X could be 2 pi over 3, or x could be 4 pi over 3. So those are the answers when x is between 0 and 2 pi. But we can also take those answers and add on copies of 2 pi. So we could say x is 2 pi over 3 plus 2n pi, or 4 pi over 3 plus 2n pi, where n is an integer. Is that okay so far? Okay, so we've actually got 4 different things going on. We could have x equals pi over 2 plus 2n pi. We have x equals 3 pi over 2 plus 2n pi, and then 2 pi over 3 plus 2n pi, and 4 pi over 3 plus 2n pi, where n is an integer. Did anybody have any questions on that one? Okay, then we're going to go ahead and take a look at another quadratic one. We want to solve 2 sine squared x minus 5 sine x plus 3 equals 0. So we can again do a substitution. We can say u equals sine x. So this equation becomes 2u squared minus 5u plus 3 equals 0. Okay, and this one I think we can factor it. So we're going to factor, and we need a 2u squared. So we're going to have to do a 2u and a u. And then we need to end up with a plus 3, but a minus 5u. So that means that both of these will have to be minuses. And then we need to think, how do we get that plus 3? Well, one of them will have to be a 3 and one will have to be a 1. So let's try putting the 3 here and the 1 there. Okay, so if we multiply it out, we get 2u squared, we get plus 3. So that looks good so far. And then we're going to get a a minus 2u, and a minus 3u, and that makes minus 5u. So that works. Okay, so we've got it factored, and now we have two things being multiplied together equaling 0. So either the first factor is equal to 0 or the second factor is equal to 0. Right? So if 2u minus 3 equals 0, that means 2u equals 3. Over here, if u minus 1 equals 0, that means u equals 1. And if 2u is equal to 3, that means u equals 3 halves. Right? Over here, let's see, what was u again? U was equal to sine x. So we can go ahead and rewrite this as sine x equals 1. And then down here, we have sine x equals 3 halves. Okay, so if sine x is equal to 1, then x would be pi over 2 in the interval from 0 to 2 pi. If sine of x is equal to 3 halves, what would x be? This has no solutions. Right? Sine can never be bigger than 1. Oops, those should say less than or equal to. So I'm going to write less than or equal to like this. Sine of x cannot be larger than 1. So there are no solutions to this first equation. The second equation does have solutions. We can say x is pi over 2 plus 2n pi, where n is an integer. Okay, so there was a question about this 0 to 2 pi. So basically, I always first think about solving my equation from 0 to 2 pi, because that's just the basic unit circle that we've got. And so I can look quickly at my unit circle and see that the only place on the unit circle where sine of x is equal to 1 is at x equals pi over 2. So I'm always going to first start by looking from 0 to 2 pi. And then once I've answered it there, then I'll take those and I'll add on 2n pi. That make sense? Okay. Ready to look at the next part? So the next one we want to solve, cosine x is equal to negative sine of negative x. And we've got a formula about the sine of negative x. So since the sine function is odd, the sine of negative x is equal to negative sine x. Oh, okay, that's fine. So the question was about where does the 2n pi come from? Anytime we have a solution between 0 and 2 pi, we can go ahead and add 2n pi onto that. So we're basically saying, so up here, since we know that pi over 2 works, we can do pi over 2, we can do pi over 2 plus, and then we can go all the way around the unit circle. So we would add 2 pi on. Or we could do pi over 2 and go around the unit circle twice. So we could add 4 pi on. Or we could have that spot on the unit circle and we could go around the unit circle 3 more times. And that would be adding on 6 pi, because every trip around the unit circle, we're adding on a copy of pi over 2. Okay, hang on just a second here. So, nope, that's not what I wanted to do. Give me just a second. I'm going to look at my whiteboard. Okay, so here's my unit circle. It's not a great circle, but here's the spot up at the top, and x is pi over 2 at this spot. Okay, and the sine of x is equal to 1. So far, so good? Okay, so I know the one answer between 0 and 2 pi. So that's where I started with, was with my one answer between 0 and 2 pi. And then after I find the answers between 0 and 2 pi, I want to get all the other answers. So if I'm right here, I can go all the way around my unit circle and come back to that point. And so when I go all the way around the unit circle and I come back, I've added on 2 pi. And then I could add on 2 pi again. So I could make 2 trips around the unit circle. Yeah, there's infinite answers. That's right. Exactly. This is how we can express that there's infinitely many answers. Exactly. Does that help a little bit? Okay, so I'm going to go back over to my other screen. Okay, so yeah, we've got infinitely many answers. So let's go up and take a look at my previous answers. Okay, so on my first problem, I was looking at solving cosine x equals 1. And I saw that there were a lot of places on my circle where cosine of x was equal to 1. There's only one, well, there's only 2 answers between 0 and 2 pi, okay? But if we don't have this restriction, there are infinitely many answers. And those infinitely many answers will always look like 2 times pi times n. So I wrote out several of them here, but if I kept writing, I could keep going forever, okay? And then for part C, I solved the sine of 2x equals 0, and I got several different answers. And then I wanted a way to succinctly write down that infinite number of answers, okay? And then on the next one here, first, we solved from 0 to 2 pi, and we got 2 answers that were between 0 and 2 pi. And then, when I'm not restricted to 0 to 2 pi, I can go ahead and add on. I can start at one of my answers, and I can add on 2 pi, or I can add on 4 pi, or 6 pi, etc. Yes, I'm always going to start with the restriction and then remove it after I find the solution in that restriction. Is that okay? The restriction's always going to be 0 to 2 pi, and we'll look at some problems in just a minute, okay? All right. Any other questions? Okay. So now everybody's good with example 4? Ready to look at example 5? Okay. So on example 5, we are trying to solve cosine x equals negative sine x. And we know that cosine x equals negative sine of negative x. We know that sine of negative x is negative sine of x. So now this equation turns into cosine x equals, and then I have a negative that was part of my original equation. And then I'm going to replace sine of negative x with negative sine x. So I've got 2 negatives, one negative from my original equation and one negative because of this identity. Okay? And those 2 negatives will cancel each other out. So we get cosine x equals sine x. You might be able to just think about the points on the unit circle where cosine x is equal to sine x, or you could divide both sides by cosine x, and you get 1 is equal to sine x divided by cosine x. In other words, 1 is equal to the tangent of x. So we've got 1 equals to the tangent of x. So first of all, let's think about in the interval from 0 to 2 pi, in the interval from 0 to 2 pi, what are the solutions? X would be pi over 4, and the other solution would be 5 pi over 4, right? So we've got our two answers. And so then without the restriction, X is going to be pi over 4 plus 2n pi and 5 pi over 4 plus 2n pi, where n is an integer. Okay, now tangent's a little bit special because remember the period for sine x, cosine x, secant x, and cosecant x is 2 pi. The period for tangent x and cotangent x is just pi. So we could have, actually, because this is tangent, we could have just done the restriction zero to pi. So on that interval, the only solution is pi over 4. And then we can add on copies of pi to that. Because notice that pi over 4 plus pi gives you 5 pi over 4. Does that make sense? So for tangent and cotangent, you're going to use the restriction 0 to pi. That's right. And then you'll add on, you can just add on, copies of n times pi, because the period is pi. Is that okay? All right. We're going to go ahead and get started on the next one. Okay. So we have 2 sine squared x plus 3 cosine x minus 3 equals 0. This one is a little bit more complicated because it involves a sine and a cosine. And in fact, it's got a sine squared. So I know our last one had a sine and a cosine, but it didn't have any square. Oh, can you go back up? I'm back up. Is this what you wanted to look at? Example 5?
Yeah.
Okay.
Okay, I'm good. Thank you.
You're welcome. Okay. So down here, we've got sine and cosine, and sine is squared. So that's not a good thing to have. We need, if we've got something squared, we only want to have one kind of trig function. But remember, sine squared of x is equal to something. So remember, sine squared of x plus cosine squared of x is equal to 1. So that means sine squared is equal to 1 minus cosine squared. Makes sense so far? So I'm going to replace this sine squared by 1 minus cosine squared. So I have 2 times 1 minus cosine squared of x plus 3 cosine x minus 3 equals 0. Is that okay so far? Okay, so I'm going to go ahead and distribute the 2. So I have 2 minus 2 cosine squared of x plus 3 cosine x minus 3 equals 0. And I've got this 2 and I've got this minus 3. I can combine those together. So I have negative 2 cosine squared of x plus 3 cosine x minus 1 equals 0. And I would like to not have a negative leading term, so I'm going to multiply both sides by negative 1. To get rid of my negative out in front. So that becomes 2 cosine squared of x minus 3 cosine x plus 1 equals 0. Is that okay so far? Next, I want to factor it. Are you guys okay with factoring it like this, or would you like to do a u substitution? Anybody care? I'm going to try to factor it the way it is. Let me know if you don't like it. All right, so I need 2 cosine squared. So I'm going to need 2 cosine x and cosine x. That'll make 2 cosine squared. And I'm going to need a plus 1, but a minus 3 cosine. So I think the only way to do that is to have a minus 1 and a minus 1. So let's just double check and make sure this works. So we get 2 cosine squared x, and we get a plus 1, and we get a minus cosine x and a minus 2 cosine x. So that gives us the minus 3 in the middle. Does that look okay so far? All right, so we're multiplying 2 things together and we get 0. So that means 2 cosine x is equal to 0, or, 2 cosine x minus 1 is equal to 0, or cosine x minus 1 is equal to 0. All right, well, if cosine x minus 1 is equal to 0, that means cosine of x is equal to 1. And over here, I can add 1 to both sides. 2 cosine x equals 1. Here I'm going to divide both sides by 2. Oops, I'm missing my x. I'll divide both sides by 2. I get cosine x is equal to 1/2. And then here, if cosine x is equal to 1, there's only one solution between 0, well, there's 2 solutions between 0 and 2 pi. So 0 to 2 pi, x is going to equal 0 and 2 pi. And on this one, if cosine of x is equal to 1/2 in the interval from 0 to 2 pi, x could equal pi over 3 or 5 pi over 3. Does that make sense so far? All right, so putting everything together, we have x is equal to 0 plus 2n pi, pi over 3 plus 2n pi, and 5 pi over 3 plus 2n pi, where n is an integer. Just notice I'm missing my p right here for pi. You might be wondering why I didn't do 2 pi plus 2n pi, but that's actually 0 plus 2 pi.